Okay, welcome back to the third day of Geometry and Calculus conference, and it is our pleasure to have Professor Mihai Păun at Bayreuth University, who is going to talk about Hermitian-Einstein metrics in singular settings and applications. And Mihai.
Well, thank you very, very much for the invitation. It's really a great honor to speak in this very nice conference. So basically, what I would like to do is to explain to you a few things about a couple of papers I have with these people here. The paper will be referred as a C++, C from Zhao, and then the rest of them. And the second one with Henri Ganancia. Now, don't be impressed by the number you see here. 121 is just what the number of times I have to click, and not the number of slides that will follow. So let's see now here. Here is the plan for the lecture. So let's go ahead and start with the preliminaries. So we have a compact Kähler manifold to start with, and rank R vector bundle on it. And then I guess you already encountered this notion many, many times, at least in this conference, the stability in the sense of slopes. It's the usual one. And then in this context, there is a very famous result due to Narasimhan-Seshadri in dimension 1, and then successively by Simon Donaldson and Uhlenbeck-Yau, saying the following. Now, if the bundle is stable, so if we have this condition, then there is a very nice Hermitian counterpart. So there is this Hermitian metric on E, such that the contraction of the curvature form is simply the multiple of the identity. So this is a constant, which of course you can compute it by taking the trace in this equality here. And now, one of the important consequences of this equality here, the existence of this metric, is that so the stability implies the so-called Kobayashi-Lübke inequality, which is the one here between C2 and C1 squared. Now, what I will do in the next minutes is that I would like to somehow generalize this in singular setting. So that is to say, establish an analog of these results. In case of X is simply a normal and compact Kähler space, and E is a torsion-free coherent sheaf. As for my motivation in doing this, I will come to this a little bit later. Let's now just go through the main objects that will appear. In the first place, I have to make as precise as possible for you what would be a metric on a coherent sheaf. So there are many, many competing definitions for that. And then, so let's see which is the one I will use here. Now, X is a normal compact complex space. And then I assume it endowed with a Kähler metric in the sense of graph. That is to say, X is a union of analytic spaces, A alpha, which can be embedded in some Euclidean space. And then I assume that my metric omega is the global object, which locally comes from out of space. So locally comes from this U alphas here, which are open subsets in the Euclidean spaces. Okay. So it's not just defined on X. I mean, okay, globally, yes, but the gag is that it comes from smooth and pluristable function on these open subsets here. And then now let's see. Okay. Then if I'm giving myself a coherent sheaf on X, then locally on this A alphas here, I can write a short exact sequence like this. Those are powers of the structural sheaves. And then let's assume that F is torsion free. So then even if X is has singularities, but is nevertheless normal, so then there exists some small subset XF inside X, codimension of the complement Okay, so xf is big. Codimension of the complement is at least 2, such that the restriction of f to this big open subset is a vector boundary. Let's call R the rank of f. Okay, so then this complement here would be simply the f singular. And then, so as we teach our students that a metric on a vector boundary is simply you do whatever you can on a trivialization and glue everything by a partition of unit. Well, we will do the same here. So a metric for me is simply locally induced by this short exact sequence. That is to say, as a quotient metric, where here the metric I'm giving to myself is simply the flat one. And then we have a perfectly well-defined notion of quotient metric, so induced here on F. Of course, we have to exclude this subset, okay? And we globalize this local construction by a partition of unit T. Wonderful. And so I computed here an example for you. So if we give ourselves this sheaf here, then well, we have the usual resolution given by these maps. And then if you do the calculation of what I said here, the norm of, for example, this section of f is simply given by the expression here. So you see, you have some degeneracy occurring where f is not a vector boundary, that is to say on this set here, given by the sum of the squares of the zi's, right? Fine. And then the next step is to look a little bit into the important result of boundary and CU. So let's say that now we put together the singularities of x and the singularity of the sheaf f. And then given this, we can construct a function, let's say phi z, which locally looks like the log of the sum of the squares of fi's, absolute value squares of fi's, and fi's are the local equation of z, right? So the fact that this is a global analytic set tells us that those local expressions, they piece together nicely and then give us this sort of function. And then, of course, the notion of a slope in this context still makes sense. We simply integrate the over x regular this quantity here, and I put here C1 of f to in a rather ambiguous way because we are integrated over an open subset, but it so happened that this is well defined. And then let's introduce a further notation. So x0 should be the complement of these bad guys here. And then in this context, the first result I would like to mention is the following. So assume that f is endowed with a metric that I mentioned before. So given by those local resolutions, is a coherent, stable, and torsion-free sheaf on a normal Kähler space. And then we can construct a metric hf, which differs from the one we have by the exponential of some endomorphism, right, on f, so where f is a vector boundary. And this has the following properties. It is smooth, as in the usual case, and satisfy the Hermitian-Einstein equation on the open part. Moreover, we have some estimates, not fantastic, but not too bad either, in the sense that the difference between these two metrics, so that is to say the exponential of the endomorphism, in the first place is bounded from above by a uniform constant, which is good, but then the lower bound is a bit less fantastic, has some zeros, and shouldn't on x0. Nevertheless, so the virtue here of this first point is that the constant is uniform, right, on the open part, on some open subset. That's what is the content of this first point. And then we have the usual other estimates in this context, that is to say the derivative of S, the covariant derivative of S is almost in L2, if provided that we divide here with this function. And then more important, that the curvature is in L2. Okay, so So somehow, yeah, this is the result we get, and of course, there are many results on like on this type in the literature. So as you most likely know, I'm pretty new in the field, so I'm very much sorry if I misquote or if I don't quote some of the people's work. But then, so starting with the work of Banda and Siu, who proved this in the context of X non-singular, and then these days Mitchell-Falk, which did it for orbifolds, and then Chen Wentworth, who proved that the same sort of theorem may be a little bit less precise. So what I will do next is...
Mihai, can I ask a question?
Please.
Yeah. Do you have a uniqueness statement?
No. For the moment, no.
Huh. Interesting.
So
okay.
As you will see in... I mean, okay, so maybe... No, in the sense that I haven't considered this question, but given the way we prove these results, it's not automatic. So definitely you have to do something to get uniqueness. Yeah.
I see. Okay, thanks.
Yeah, sorry. So we proceed in a very classical way, meaning as suggested by Banda and Siu, using this result of Rossi, which treats the singularization of sheaves so that there is some modification of X, which basically resolves the singularities of X and of F. So this one now is a compact Kähler manifold, and pi restricted to the open subset where nobody is a singular. This is an isomorphism. And the exceptional divisor has a simple normal crossing. And then the pullback of F, which is a very unpleasant operation to do, but when you mod out the torsion, then this is locally free. Right, so this is the result of Rossi. And then first remark is that the stability with respect to omega turns out to be equivalent right away with the stability of E with respect to the pullback of omega. But then one should be careful that even so, this 1-1 form on X hat, it is of course semi-positive. It is strictly positive on in the complement of the exceptional divisor, but then of course it has some zeros. Nevertheless, it's good enough to measure the degree of sheaves and vector boundaries with it, and it is in this sense that it's stable. Now, as I hope you will agree with me, even more important than knowing results is to know what's in the proof. And then it's so happened that as the consequence of the proof of theorem of Rossi, we can derive the following. Now, the metric that I mentioned before induces actually a smooth metric on this boundary E, meaning that if you look at the way the theorem of Rossi is proved and how this space X hat is constructed, well, the pullback of the metric that we have somehow extends smoothly and give a metric on E, exactly as the boundary E itself can be seen as the extension of the vector boundary F on X0. And then, so something a little bit more precise in this sense is that if we get any local section of F, then by taking the inverse image via this map pi, we get a section of E at least on some open path. But nevertheless, we can compare the two like this by uniform constants. So what's remarkable here is that this constant is independent of whether we are close or far from the exceptional divisor. Okay, so we can compare perfectly the two. And then another consequence of the choice of this metric and of the proof of the theorem of Rossi is that actually the curvature of E endowed with this metric pullback, if you want, is bounded by the inverse image of omega times the identity of E, which I think it is a remarkable thing. So normally this is a 1-1 form with values in the endomorphism of E. So here the normal 1-1 form that should be, well, it should be some metric on X hat, but then we get something better, namely, if you want, when you restrict this on the fibers of this map, so we get you get here 0, so a semi-positive 1-1 form. Of course, there's no big mystery of that. We all know that when we take the curvature of the quotient, the curvature is increasing, and that's exactly what explains this inequality here. Fine. So now, of course, we will proceed by approximation, as suggested in the paper by Bander and Seo. I think is the last remark in the article. So we can construct a metric on X hat like this. We simply take the pullback of a metric on X and correct it in the direction of the where it vanishes, right? We can do that. It's absolutely classical, absolutely well known. Why I say classical all the time, I don't know. And then that's the fact here, that we can choose epsilons, the epsilons in such a way that this is a Kähler metric, right? And then let's take omega t, simply the pullback of omega plus t times this honest Kähler metric on X hat. And t would be between 0 and 1. And then a result I learned from Matej is that the boundary E is omega t stable for all t between 0 and 1. Of course, this is a result which is present in many people's work, I think, but like I said, since I learned it from him, so I just mentioned his name there. So let me just give you a very quick account of what is inside here. Well, the point is that we have to show that there is some delta 0 positive such that the slope of any sub-sheaf G here in E is delta 0 far from the slope of E. Okay, if you look at what you have to prove, that's what you have to prove. And then, so if not, what will happen is that we will get a sequence of line bundles here in some p power of E, some semi-stereo power of E, such that the slope here converges to the one of E. So there's no such delta 0. Huh? But then let's look at sigma k, which is the section induced by this short exact sequence. So that is to say, is a section of lambda r of E tensor LK inverse, right? And then if we consider this object tk, which is the curvature of the dual of LK here, plus IDD bar of log of sigma k, the holomorphicity of this sigma k makes it that if we add some fixed multiple of omega hat, we'll get something strictly positive. And this uniformly with respect to k. So there is this uniform constant which does that. Okay. And then well, now if instead of this degenerate metric we will work with an honest omega hat, we are done, because then this family of currents is bounded. So we have a bounded family of closed positive currents, hence it converges, but then the cohomology class should be convergent as well. But this cohomology class, so here I have an integer and here I have a fixed constant times omega hat. So that's not possible. I will get equality here without taking the limit for k large enough. Okay, so the contradiction will come from there. And then, yeah, the general case is similar, but then, like I said, it's a very well-known result. So another approximation argument that we're using is that, well, now by Uhlenbeck and Yao, we get a family of Hermitian-Einstein metrics on E. Hermitian-Einstein with respect to omega t. Okay, so omega t again was the pullback of omega plus t times some strictly positive 1-1 form on X hat. And then, as of course you remember from Richard's lecture, if you take H L, the determinant of E, endowed with the determinant of the background metric here. So now consider the induced curvature form on L, and then we can solve this equation given that the integral here and here, they are the same. So we have a unique solution such that, let's say, rho, which I normalize like this, okay, with respect to the omega t metric. And then, so we consider the metric HT0, which is exactly this one, the background metric twisted with the exponential minus rho t over r. So this, why we are doing this, so if you remember the proof of the result of Ullenbeck and Yau, so you first start by normalizing by saying that, okay, at least for the determinant, the Hermitian-Einstein condition is satisfied, and that's exactly what we do here. Except that in our case, everything depends on t. It's terrible. And then, so we can, if you want to express our Hermitian-Einstein metric here as follows, as a multiple of this normalized metric HT0, right? Times exponential RST. And the whole point of all this situation is to say that now the trace of this endomorphism is pointwise equal to 0. Okay. So it's yeah. So now, of course, what we want to do is to simply take the limit as t goes to 0, and then show that actually what we get is, well, in the first place makes sense and satisfies the requirement in theorem 1. And then in what follows, I will explain to you okay, the main difficulty in doing this is that, in order to take limits, you have to make sure that you have some estimates, and then the geometric invariants which are needed for this family of manifolds, they are to be bounded, right? And then, so let's see, what do we have at hand about this family? Well, in the first place, in the complement of the exceptional divisor, things are fantastic. The geometry is uniformly bounded on any compact subset here, so we don't have any trouble with that. Now, if X is non-singular, then the Sobolev constant of this family, right? So we know that for each t we have a Sobolev inequality, but then the Sobolev constant that comes into the picture may vary with respect to t. And then Banda and Siu show that actually that's not the case if X is non-singular. So then we have a uniform constant. That's very important because, as you will see in a moment, the Sobolev inequality is very important in this whole story. Now, in general, so if X is no longer a manifold, then this was only proved very recently by Guo, Fong, Stuhl, and Song, like 1 year ago. Well, so all in all, we do have a Sobolev inequality which is uniform with respect to this family. Now, all in all, there exists a constant such that omega t is uniformly bounded from above. That's absolutely clear. But then there is another property which this family of metrics satisfies, despite of the degeneracy that we have, is that if we take the log of the quotient of the two volume elements, so this is a function, right? Then we can look, given this expansion that we have here, we can bound it by minus log of some powers of t to the alpha times this, where the first one corresponding to alpha equals to 0 is a sum of the squares of holomorphic functions, not all of them 0, right? Because for t equals to 0 is simply the Jacobian of the inverse image of omega, right? And then it follows that the pth power of this function times the volume, so times the metric omega t to the n itself is bounded, and this is true for any p positive. Okay, so this omega t has zeros, but nevertheless it's not too bad, right? So we have this property here, which will come into the picture now. So again, so the uniformity properties of this family of Kähler metrics is crucial, and what we have at hand is not great, right? Because there are many important geometric invariants which are missing. But then something wonderful happened. Guo and Sturm, they came up with a very general mean value inequality, which happened to be exactly the result we were needing in order to move on with this, with the proof of the result. So the theorem is as follows. So we have V, which is in L1, arbitrary function, which is C2 differentiable where is greater than -1, and such that the second derivative, so the Laplace, I'm sorry, of V with respect to omega t is greater by some constant which we denote by -a. And then we have that the supremum of V on x hat is bounded by a universal constant, meaning that is independent of t, times the 1 plus L1 norm of V. Okay, so this is really a wonderful result in the sense that usually, I mean, for each t fixed, you do have some constant here because you know everything about the green kernel, right, of omega t for each t fixed. But then the point is that the dependence of the green kernel with respect to omega t is very, very nonlinear. So it's extremely difficult to control in general what's happening. Nevertheless, these people managed to prove such an inequality, which, like I said, it's exactly what we were needing. And in particular, thanks to this, we can simply forget about the Sobolev constant. And what I also should say is that the hypothesis, if you look at so here I just extracted the result that we need in what follows. But then if you look at the original presentation, original result here, you will see that the hypotheses are extremely flexible, and then they match our geometric context, not only ours, but many. So now the plan is to see how we can get the estimates for the objects coming into the picture in the metric h t infinity, now Hermitian-Einstein metric for t positive, for this object, for the scalar, and for the endomorphism as t. So let's look first at the family of functions here, which we needed to normalize the determinant metric. So remember that we have this data, so the curvature of AE with respect to the background metric is bounded like that. And then, I recall that rho t was the solution of the normalized solution of this Laplace equation here. And then, well, we have the following lemma. So there's a positive constant c such that for every t in 0, 1, we have this inequality. So rho t is bounded from below universally in terms of is L1 norm, and the bound from above is a bit less precise, but then is bounded by constant times log 1 over SD square plus the L1 norm of rho. So we have the constant which is independent on t times the log of the equation of the exceptional divisor, which comes into the picture here. Okay, so again, the point here is the independence of this constant with respect to t, because ultimately we want to take the limit. So let's look here how very quickly how the proof goes. well, in the first place, this theta L here was the trace of what we have here. So it's definitely greater than minus C times the pullback of the metric. So in particular, greater than minus some constant times omega t. And then when we take the trace with respect to this very metric, so then here we get that the trace of omega t with respect to of theta L with respect to omega t is bounded from below uniformly. Well, and then if I look at this equality, what we get is that the Laplace of minus rho t is bounded from below by some constant. And then this inequality follows right away from the result I was mentioning. Okay, so you see, by applying these results, we get right away the estimate we were after. And then let me try to explain why we have this additional degeneracy here in the estimates. Well, now when we want to consider the upper bound for theta L, now theta L is 114 on x hat, so I don't have an analog inequality to this one in the other sense. So the best we can say is that some constant times omega x hat. But then in this omega x hat, well, I write it here in a rather imprecise way. So it's the inverse image of omega plus IDD bar of the log of this SD square, right? So if you look at the way we defined it, this metric, it's something which looks like that. In any case, so, and now given that this one is smaller than omega t, so we get that, right? The constant times omega t plus the Hessian of the log of SD square, the norm of SD square. So then when we take the trace with this, we contract with respect to omega t this theta L. What we get is simply here we replace this with a constant plus the Laplace of the log of SD square. So all in all, the Laplace of rho t plus this function here will be greater than minus C. Okay, so this disappears. Logarithm of SD square precisely because of the shape of the metric on the blow up on the decimalization of the x. Okay, so you see that here we use the full force of the GPS, namely that this is not smooth any longer, but it is smooth where is greater than -1. Okay. Fine. So, and as you can easily guess, we will do the same sort of arguments for the family of endomorphisms. So we have this we have this HT which looks like that, all in all. And then the inequality that, so the analog of the C2 estimates for the Hermitian-Einstein setting is like that. So the Laplace of the log of the trace is bounded by from below with this quantity, by this quantity. And then here, again, we use our lower bound for the curvature of E, that is to say this term here. And then all in all, we infer that the Laplace of the logarithm of the trace of HT, so the endomorphism we are interested in, is bounded from below by a uniform constant. Okay, so again, so here what is crucial is that we see T all over, but not on the right-hand side. It's a uniform constant. Fine, so then again, it follows that the logarithm of this, so that the supremum of this function here is bounded by a constant plus its L1 norm. So everything depends on T other than the constant here. And then so now with this, that's exactly what is needed in order to complete the proof. And the main step is as follows. So it is a fact that actually we can improve these estimates and simply say that rho t is bounded between these two constants, and the trace of ht is bounded from above. Okay, so now all all that I feel obliged to say, given that I'm sure you follow Richard's lecture, and you know that how such a thing is proved by you argue by contradiction, and so the proof is similar to the usual arguments, but one have to be careful with the fact that the metric omega t varies. Okay. So somehow the theorem 2, together with the Hermitian-Einstein condition that we already have, so those are exactly the estimates that one needs in order to obtain the theorem 1 that I was mentioning before. Fine. Now let's move to another topic, which is somehow put some more structure on X, not just a normal Kähler space, compact Kähler space. So let's assume that there is a W inside X of codimension at least 3, and then such that in the complement of this W, we only have quotient singularities. So that is to say, for each point in this complement, we can find some open subset which is uniformized by open set in Cn mod finite automorphism group, right? So this is what is happening if X has so-called log terminal singularities, but I think yeah, so we have some bad points only in codimension 3, in codimension 2, so the singularities are at most quotients, or pretty much the same as smooth. So the example and somehow motivation for the next part of the talk is like this. So let's look at this example, usual one, the C0 times C2 modulo plus minus identity, and then this map from C3 to C4 given here embeds our germ of threefold in C4. And then two observations are in order, is that if I restrict the Euclidean metric here to X, well, what do we get? Is Z square, which is okay, but then I get something which looks like that, right? Right, so, and what I would like to say is that the natural metric on X would be rather this one, right? Because the inverse image via this embedding is Euclidean. Okay, so there is a discrepancy between the smooth metric that we consider on X, which is this one, and the natural metric, which would be which would be somehow, which would respect this orbifold structure here. And then so assume that X has this sort of geometry. So outside codimension 3, I only have nice singularities. And assume that moreover, F does the same. So in the complement of this W, this is a so-called orbifold vector bundle. So on the uniformizing subsets, I have an honest vector bundle such that the inverse image of F, at least restricted to the, whereas a vector bundle is the same as E. And then, so what I want to say is that this context is actually very natural in birational geometry. So, and assume that moreover, F is stable with respect to this class. And then the question is to construct a metric HF on F, which is Hermitian-Einstein, which with respect to some well-chosen representative of this metric, and in such a way that this metric also respects the orbifold structure that we have on F. Okay, so we are greedier and greedier, and then so let's look at the orbifold version of term 1 that I want to present next. So in the first place, so omega W, remember that it was the set of, let's call them bad singularities. We don't know anything about them. And then, but what we can do is to consider some open subset here, omega containing them, and then to construct some continuous function from X to R in such a way that this metric, omega plus IDD bar phi, has the following properties. So outside the open set omega, so again, so outside this, we only have quotient singularities, and I want this object that I have here to have orbifold singularities, right? That's a legitimate wish, and then we can construct such a phi. But then I also want that if I shrink a little bit this omega, so near W, I want my metric to be the one I fixed at the very beginning. This is also possible. Okay, so somehow this omega orb here is the notation is very misleading. It's somehow interpolating between the honest orbifold metric and smooth metric we have on X. So the reason why we cannot have anything better is that we ignore everything about the singularities here, right? So we don't have any model, as in the case of the quotient singularities. So the best we can is, well, simply to do this interpolation. And then in this context, we have the following. So if we have, well, I put KLT here, meaning that this property is satisfied, and F is orbifold vector bundle, and I assume it's stable with respect to the class of this metric. And then we can construct Hermitian metric on F restricted to X0 with the following properties. The first one is that is smooth and satisfies the Hermitian-Einstein equation here. And moreover, it has quotient singularities, but only on this in the complement of this omega, right? Where the reference metric has orbifold singularities. And then the same type of estimates as in theorem 1 hold true. Okay, so somehow the trouble, if you want, with this theorem is that we don't get honest orbifold metric on F. We only know that this metric has orbifold singularities in the complement of an open subset near, which is near the bed loss at W. Now, just 2 words about the proof. What really matters is that despite of the fact that here we have some singularities in this omega orb, nevertheless, the volume element is in LP for some p bigger than 1. Okay, that's the main property of this metric, which allow us to, well, first of all, to approximate this by using Monge-Ampère theory, and then to be able to apply again the result of Guofeng and Sturm in order to get the same estimates as before. Uniform for the approximation of this, and then ultimately to take the limit. Okay, so modulo this additional difficulty, the results in recent progress in Monge-Ampère equation allow us to basically follow the same sort of proof. It's really very, very impressive, the result what these guys did. Okay, so now let's look a little bit at the generalization of the Kobayashi-Lübke inequality. So we have X and F as new theorem 3. And then what we can do is to use this metric HF, the one having quotient singularities in the complement in this X minus omega, to define the Chern forms theta k of F and H, right? So by the usual Chern-Weil theorem. And in particular, we have the discriminant, which is well defined 2-2 form, but again, it's only defined here on X0. And then, so the main question which occur here is that this is a 2-2 form on X0. What are its numerical properties? Because we would like to say something about the positivity of this, the numerical positivity of that in the end. Now, by the work of the people I mentioned before, what one can say is that the discriminant associated to E wedge the omega, the inverse image of omega to the power n minus 2 is semi-positive, where this is the singularization of F. But actually, it so happened that these representatives here and what we have here, they disagree. They are not the same. And it so happened that in birational geometry, it is rather this which which encodes the meaningful information for them. Actually, this was the question that somehow get me started in this field. It was formulated by Campana, Hurling, and Peternel. So assume that in this context, the dimension of x is equals to 3. So then we only have W, which is a finite set of points, which are the bad singularities for which we don't know anything. So then consider a function theta such that if I take my metric omega plus IDD bar of theta, this is 0 near W. I can assume that this is 0 on this set omega that I mentioned before. And then the conjecture was that the integral over the regular part of x of this of the analog of this discriminant of F wedge omega theta is semi-positive, right? So and somehow the motivation, the main motivation for this question comes from the project of Thomas Peternel, extending the minimal model program in the Kähler case, and then that's one of the question coming into the picture in the proof of the abundance conjecture in dimension 3. So maybe I can say something more about it. So you see, if you are in the projective context, then things are slightly easier because, I mean, especially if this class is a class of ample line bundle, then you can use hyperplane section, and then the surface that you get here, we only have quotient singularities, right? Because this hyperplane will avoid the bad guys here, and then yeah. You will, and on the space with quotient singularities, things are very well understood. They're pretty much the same as in the smooth case. But then everybody who ever tried to integrate on an open manifold knows that this is usually really trouble, right? So that, for example, Stokes' theorem will not work. I mean, of course, it works perfectly, but then you have to take care of the boundary terms. And then, so let's see. What happened here is that in our initial art paper, we treated some particular cases, and where if the dimension of x sing is 0, or if x admits the so-called partial resolution of singularities, which is a result which was established in the meantime. But then in our work with Henri, we show that actually this conjecture is true by purely analytical methods. And this is what I would like to discuss next, in the remaining 5 minutes, let's say. So the main steps in the proof are as follows. So consider this metric omega orbifold. And then HF is the metric given to us by theorem 3. And then first thing is to say that actually this HF is quasi-isometric to the, let's say, H orb so you see, we control this metric HF in the complement of x minus omega, but then in omega minus W, this part of the complex space comes into the picture, and we don't know much about this one there. But still, the first point is to show that this one, the situation is not too bad. We don't have C2 estimates, but at least at the C0 level, things are okay. And then, so that is, yeah, HF is close to the orbifold metric. And then the second one is that despite of what I said before, the integrating on the open subset, this object, this 2-2 form on x0 can be seen as a current, and this is closed in the following sense. So I put closed in quotation mark because it's not really closed in the usual sense, but so it only gives 0 when you integrate it against the d bar of alpha. So this would be closed if I can do this for every alpha, but actually in our situation we have to impose that the supremum of alpha with respect to the metric we have at hand and to its d bar is finite. Okay, so here it should be not x, but x minus, well, x regular. Okay, so that this integral makes sense at least. Fine, so if we have this at hand, the rest is pretty simple. So remember that we have to evaluate this quantity here. Okay, and this one involves, so I can of course multiply with some cutoff function which is 1 almost everywhere and 0 near the singularities, near the points. And then this I can separate it into 2 parts. This one I insert my orbifold metric, and the second one, which would be this 2-2 form wedge DDC of so this is my the potential of the orbifold metric. And then yeah, so this chi epsilon is a Semmelov-Tarkasian function converging to this the identity function of x minus pi, the bed set. Now this integral is positive, as we know from the usual differential geometry calculations, because this is a Hermitian-Einstein metric, this HF with respect to omega orb. And then for the second one, this is exactly where the point 2 comes into the picture. We can integrate by parts here, despite of the fact that we are this one is not compact. So we can integrate by parts, and then the integral we have to evaluate becomes something like that. And finally, the last integral will converge to 0 as one wishes, is exactly for the following reason, is that so for epsilon small enough, the differential of this chi epsilon will tell us that we integrate on theta equals to 1, so I don't see any of this term here. And then this is the potential of the metric near the point P, so I can take it of the form of order z square, where z is the coordinate on the ambient space. So the differential that I have here will compensate the differential of the chi epsilon, the norm of this one. So all in all, this term here will be bounded. And since you integrate something which is L1, this one, on something on a part of the manifold whose volume goes to 0, then it can only converge to 0. Yeah, so this is the main part of the proof, the fact that we can integrate by parts here. And the most important thing, many thanks for the invitation. So I think I will stop here. Thank you.